Let's look into the first question. Define vector space and subspace of a vector space. Vector space is nothing but it is a non-empty set V where it undergoes the addition and multiplication with some properties. We must look into that. U, V and W are in V means vector. C and D are means scalar, which are in scalar. So first property is if U plus V is in V for all U comma V belongs to vector. Here this is a closure property. U plus V is equals to V plus U. This is a commutative. It is under addition. This is the associative property. We have U plus V plus W is equals to U plus V plus W. We all know that. And there is a vector 0 in V such that U plus 0 is equals to U, which is the identity property. And also we have it is under addition, and this is the inverse property. U plus of minus U is equals to 0. This is the inverse property. So from all this we can say that we have a group properties. In the group theory we have learnt the group properties, where for group plus commutative, which is called as an abelian. So here V under addition, it has to be an abelian. In this we will get all these properties 1, 2, 3, 4 and 5. 5 properties which comes under addition, vector addition, which has to be an abelian. Now 6th, 7th, 8th, 9th, 10 comes under the scalar multiplication, which U is vector, U is in vector and C is in scalar. Which is in scalar we will denote by field, okay, F. So U belongs to vector and C belongs to F. Cu is in V. And second one, C into U plus V, which is equals to, it comes under the U and V belongs to vector, and again C belongs to field. C into U plus V is equals to Cu plus Cv. And C and D are the scalars. We all know that C and D are the scalars, and U here it is a vector. C plus D into U is equals to Cu plus Du. And same thing, C and D are the scalars, U is a vector. Cd of U is equals to C into Du. 1 into U is equals to U. This comes under the scalar multiplication. Okay, this is comes under the scalar multiplication. If 10 properties hold, this comes under the vector space. Now we will look into the subspace. A subspace of a vector space V is a subset H of V that has 3 properties. First, before going to the subset, let us talk about a set, normal set and a subset. If 1, 2, 3, 4, it is a set. What is a subset? Subset, it will become 1, 2 or 2, 3 or 1, 2, 3. These are all become the subset. In the same type, if V is a vector, V is a set, okay, it is a V is a vector space is a bigger one set, then H is a subspace. In that means this is a bigger one, in that you have in this vector only you need the smaller elements for the H. To understand this H, we have 3 properties. First one, the 0 vector of V is in H, and for UV in H, U plus V is in H. If this UV belongs to H, then U plus V also belongs to H. Next one, if U belongs to H and C belongs to scalar, then Cu belongs to H. This is the third property. If these 3 properties satisfies this, then H is said to be a subspace of a vector space. And second question, given V1 and V2 in a vector space V and let H is equals to span of V1, V2, show that H is a subspace of V. Now we have discussed about the definition of a subspace, right? To prove that, first of all, here it is given that H is equals to span of v1 and v2. Span of v1 and v2 is nothing but the combination of linear combination of v1 and v2. So now here I will take for subspace we need to prove that 0 belongs to H, and next we have to prove that if uv belongs to H, then we have to prove u plus v belongs to H, and third one u belongs to H and c belongs to F, then we have cu belongs to H. So for these things we need u and v, right? So I'm just writing in the form of it is belongs to H, means it has to be the linear combination of v1 and v2. So I will write u as a s1 v1 plus s2 v2 and v as t1 v1 plus t2 v2. First condition, 0 belongs to H. 0 belongs to H means we have a 0 vector. First one 0, it can be written as in the combination of linear vectors, linear combination of v1 and v2, right? It can be written as this. So by this we can say that 0 vector is in H, and second one u belongs to uv belongs to H, u plus v belongs to H, means first we have u plus v, which is equals to, what is u here, s1 v1 plus s2 v2 plus t1 v1 plus t2 v2. Here we have to write in the combination of v1 and v2. So when we can write s1 plus t1 into v1 plus s2 plus t2 into v2. Now we have written in the combination of v1 and v2. So directly we can say that it is a combination of v1 v2. So it is belongs to u plus v belongs to H. Now what is the third property? It is cu. U belongs to H and C is a scalar. Cu belongs to H. We have to prove this. For this I will take Cu, which is C into what is u, s1 v1 plus s2 v2, which can again can be written as cs1 into v1 plus cs2 into v2. It can be written as in the combination of v1 and v2. So it is again which is belongs to H. Cu belongs to H. Now this three properties satisfies these conditions. Satisfies this condition. So now we can say that H is a subspace of V. Here, look into the third question. Show that H is equals to ST0, ST belongs to R is a subspace of R cube. Now, we can write this H as in the linear combination of the vectors. We have seen that, let's first suppose V1 and V2 are the vectors, right? We have seen in the previous problem. Now, we have written it in the combination of S and T separately with the two vectors 1 0 0 and 0 1 0. Now we can write it as easily as H is equals to span of two vectors, means it is a span of u and vector v, where u means 1 0 0, u means this one and v means this one. These are the in the combination of the vectors. If u and v are in the vector space R cube, then H is equals to span of u v means it is automatically the subspace by the definition, and also we have seen in the previous problem. Fourth question, prove that the intersection of two subspaces is again a subspace. Means, for example, if we take two subspaces, let's say W1 and W2 are two subspaces. Here intersection of two subspaces means W1 intersection W2 is also subspace. We have to prove this. For this, we are clearly known that W1 is a subspace. Let us look into the first property. Means if W1 is a subspace, we have 0 vector in this, right, by the first property. So if W2 is a subspace, 0 vector is also in W2 because it is a subspace. So first property holds, right? If 0 belongs to W1 and 0 belongs to W2, we can write it as 0 vector belongs to W1 intersection W2. So first one is satisfied, and next go to the second one. If W is a subspace, we can say that U comma V belongs to W1, means U plus V also belongs to W1. If U comma V belongs to W2, then we can easily say that U plus V belongs to W2. By this too, I can write it as U plus V belongs to W1 intersection W2. Second property holds. Next, we will go to the third property. What is the third property here? If U belongs to W1 and C is a scalar, then I can write it as CU belongs to W1, and if U belongs to W2 and C is a scalar, I can write it as CU belongs to W2. If CU belongs to W1 and W2, by this two combination I can write it as CU belongs to W1 intersection W2. So all the properties of subspaces satisfied. Therefore, I can write it as W1 intersection W2 is a subspace of vector. Fifth one, find matrix A such that W is equals to column A, where C is equals to 6A minus B, A plus B minus 7A, AB belongs to R. First, before going to that, we have to go through with the definition. Column space. If A is equals to A1, A2, so on, AN, then column A is defined as span of A1, A2, so on, AN. Span is again nothing but it is a linear combination of the vectors. It is denoted by column A. Now it is column A, C is given as a column space here. Now C is equals to what it is given as 6A minus B, A plus B minus 7A. Right. Now we can write it as W is equals to column A. So I am writing this in the combination of scalars. So I will write it as a W can be written as set of linear combination, right? Now W is equals to, how we can write it in the form A, I will take it separately, 6A minus 7A plus minus B and 0, right? Now I will take the vectors separately. Here A into 6, 1, minus 7 plus B into minus 1, 1, 0. Now I will write it in the combination of span as span of, I will take only the vectors. What are the vectors here? 6, 1, minus 7 and minus 1, 1, 0. So if this is W is equals to column A, it is given. I have written it in the form of the vector span 6, 1, minus 7, minus 1, 0. Okay, column A is span of A1, A2, AN, means what is the A matrix? It is only A1, only the it is a vector. So I will write it in the combination of this. What is a here now? A is nothing but 6 minus 1, 1 minus 7, 0. This will become the matrix of A.